Hello and welcome to NOV Live. My name is Shelby Dumaine, and this is the show each week where we talk to experts here at NOV on the subject that they are most knowledgeable in, and we bring that information out to you. And this week we actually have an extra special show. We have guests from outside of NOV as well here to talk about the amazing world of subsea storage. So welcome. Thank you so much for joining the show today. As you might have seen in the title or in the description, we have a panel discussion today, and we're really excited to bring you all of these great minds to talk about subsea storage. And to kick us off, I actually want to bring on first Julie Lund. She is Senior Engineer for Subsea Storage. Hi, Julie. How are you doing?
Hi, Shelby. Thank you. Thank you for this opportunity to present our joint industry project together with some of our key joint industry partners. The background for this enabling technology for using a membrane-based subsea storage solution for all types of fluids like production chemicals, enhanced oil recovery chemicals, oil, condensate, renewables as ammonia or e-methanol, is that the storage technology could be a part of a low-carbon future, a building block for reducing topside weight and capacity challenges, as well as debottlenecking brownfields and long tiebacks. So the qualification process that we're going through and this project for the subsea storage technologies, it follows the API recommended practice 70NQ, and the qualification process will be validated by ABS, which is also joining us today. The previous technology activities that we've done includes a membrane service life testing. It includes small-scale testing with a 40 cubic storage unit, 3 cubic storage units, as well as packing tests with 405 cubic storage units. So NOV has completed the first steps, and the engineering work for product validation has been done. And now the next step, as we will be showing you, is to build a submerged subsea storage system with 2 times 200 cubic storage units, and also doing some sensitivity testing with different densities with 3 cubic storage system. And we will reach a technology readiness level of 4, hopefully after this project, and it will be validated by ABS. So Shelby, actually we do have a video that I think will give us a great introduction for this panel discussion.
Absolutely. I'd love to see it. We'll get that video up here to learn a little more. There it goes.
NOV is developing key components for the market, and one of these components are the subsea storage system. Our subsea storage system can store oil, it could store chemicals, or separation of produced water.
The main benefits are it's really simple system. We are making a competitor to traditional FSU systems, and of course the CO2 footprint compared to conventional systems is also a big benefit.
All right. Thank you so much for bringing that video for us, Julie. And I know we're going to be showing a few little clips from it here or there and talking more about that later in the show. But before we do that, I do want to introduce all of our guests. As you mentioned, we have some of our excellent partners here on the show today. So I'm going to run through it quickly, and then we're going to let them say hello. So first we have Hamid Daiyan from ABS. We have Chris Shaw from Shell. And we have Charlie Booth from NZTC. And gentlemen, welcome. And in that order, can you go ahead and tell us a little bit about yourself and your organization? So we'll start with Hamid, sorry.
Yeah, hello everybody. This is Hamid Daiyan. I've been involved in various research and technology development initiatives with Sintef, Oil and Gas, and Baker Hughes. And in my current role at ABS, I serve as Sustainability Manager for Norway, and I'm focusing on assisting clients in achieving their decarbonization goals. And it's a pleasure to be here.
Thank you. And Chris?
Yeah, thanks. This is Chris Shaw. I'm with Shell, working here in Houston, and I'm part of our newly formed offshore engineering group. We're basically an engineering and technology development group. We do some research, but basically in technology development. My role is in the deep water hardware, so I've been responsible for looking after projects in the typical subsea production systems, hardware technology, and some fancier things like mudline boosting and in-well for wet wells, for subsea wells, in-well artificial lift, that kind of thing. Happy to be here to talk about the chemical storage.
Absolutely happy to have you. And Charlie, welcome.
Yes, hello everyone. So my name is Charlie Booth. I'm a project engineer in the NZTC, or Net Zero Technology Centre. So we are based up in Aberdeen, which is up in Scotland. So I think we've got people from all over the world on the panel today, which is really cool. So what we do is to accelerate the development and deployment of technology into the energy industry to promote a net zero energy future. Obviously, focused on the UK and the North Sea for obvious reasons. So yeah, great to be here.
Absolutely, and thank you all again for joining. And with that, I'm going to let Julie take it away. She has some questions to ask each of you. Take it away, Julie.
Thank you, Shelby, and thank you all for joining. So, Chris, I would like to start with you. So, from an operator point of view, what would you say are the pain points for brownfield developments along tiebacks, and how could subsea storage be an enabling for a field with more expanding the field with more wells?
Yeah, great question. Obviously, affordability is the key aspect here. We're always discovering assets that have a limited number of reserves. In other words, we can expect recovery at a certain level, but it's insufficient to support its own host, and therefore we look to the subsea tieback. And of late, we've been trying to increase tieback distance, and we're just trying to keep the existing hosts full. So as you know, Julie, we've got a potential deployable or deployment opportunity here for the subsea technology. And what we did, we went ahead and working with you guys, did a study looking at the technical and economic feasibility of the subsea storage concept, and came back and indeed found specific reasons to go ahead and pursue this JIP, pursue the technology development, maturation, qualification, and we chose obviously the JIP model as the way to do that for obvious reasons. More than two heads is better than one, and obviously leveraging cost and all those things, all those good reasons to join a JIP. So we're basically happy with the size and I would say the simplicity, the lack of complexity in the subsea was a chief one. Don't think we would have got through all the hazard tests that we put ourselves through during the technical feasibility. So I think it's a good technology to help us in specific instances save capital and OPEX, actually, and operational costs associated with the management of the chemicals and injection of the chemicals. And I think there are other applications that will come, and we'll talk about those later, I know, as we get more knowledge about this system and it becomes a little better known in the marketplace.
Thank you, Chris. So from our point of view, it sounds like it is a key enabler for field development, but how would you say that it's comparing to other competing solutions that you're looking for or looking at?
Yeah, we've looked at umbilical-less, which is a very strange English word for trying to replace the umbilical with a system that can take all the umbilical functionality, and that tends to be has a pretty strong role in the very long tiebacks, and that's typically gas tiebacks. So I was going to say, and then of course with the project, we looked at the best available technology that we were comparing it to is actually the control buoy or a utility buoy. And one of the early issues we had with that was, how do we maintain the hardware? In other words, how do we get onto and into the buoy and these kind of issues to manage all the maintenance of the hardware that's there, that's now on this small floating thing. And then clearly the next thing that came along was now we've got these large volumes of chemicals, and of course you're therefore continuously changing the buoyancy of the buoy itself, to the point where we were wondering whether we needed to move to a different type of technology than a buoy, move more towards a spar, more towards even active ballasting, which completely removed the chance to make it unmanned. So I think this represents a unique solution, and we're gung ho on the technology and hope that we're successful with our maturation plan. Clearly. So it competes with umbilicals, competes with buoys, and it's in the long distance, which is where we're headed with these tiebacks. Our strategy is to keep the hubs full, so we need to be looking further and further afield in order to find these target reservoirs and exploit them affordably.
Yeah. Thank you for your valuable input. So, what would you say that the key differentiators, if you could help me just to summarize it with the subsea storage technology?
Yeah, absolutely. You can imagine a brownfield retrofit of whenever we have a brownfield tieback to an existing host, there's always either a boarding valve or a separator or some kind of hardware is needed to be taken on. But in addition to that, we're often required to these other reservoirs have fluid and reservoir properties that are quite different from the original properties of the reservoir that the host was originally supporting, which can mean that we have the requirement for completely new chemistry. And in fact, when we look at some of our fields where the water cut is going to be very low over life of field, we look at an LDHI type solution, which is a relatively high volume chemical. You can imagine that adding extra chemical storage and injection capabilities on the platform is much easier when the storage volumes are low. As soon as you start to move into these higher chemistry injection volumes, for example, the LDHI, the paraffin inhibitor, the thermodynamic inhibitors, hydrate inhibitors, they all tend to use large volumes, and just not as easy to manage that in a retrofit situation. The complexity of the brownfield task itself, HSE issues associated with the task, eventually the cost, all these things play a role in driving that capex up. As you mentioned, deferment of production often can happen with the tie-in situation. So those are the kind of things that we hope to avoid. And then of course having the chemistry away from personnel, allowing us to bring it in higher volumes. In fact, if we go beyond 1,000 barrels in a replenishment situation, we can switch from totes and ISO tanks to vessel hull tanks, which is just a safer way. The lifting of totes and such like offshore is always full of risk. So to have a hard tubed connection to the platform and filling tanks that way is preferred. So all these things play a role into the decision to deploy this kind of technology.
Thank you.
Did I answer your question?
Yeah,
I got lost a bit through there.
No, I think that was very good. Yeah, I guess we as well, we see this, recognize this technology as being a game-changing technology. And also for new people joining in that haven't, that doesn't know the technology, I'll just try to summarize a little bit how it looks like. We're looking at the storage unit, the subsea storage unit that is gravity-based. It's a remote storage unit that employs the concept of a flexible membrane. This flexible membrane, it is protected by a protection structure for storage of liquids subsea. The system that we are looking at, it can be an open system or a closed system. For the open system, you have the protection structure designed ambient to sea, and the ballast water, the seawater, would then be flowing in and out of the protection structure. For the closed system, the balance fluid will come from topside. That could be treated with seawater or firefighter water, in lack of better words. And for both systems, the membrane serves as the first barrier, and the second barrier would be the protection structure. So for all our systems, they are designed with a control and monitoring system. And as Chris also mentioned, we've done extensive risk assessments of the systems. We started with working with storage of oil and condensate and chemicals. But recently, we've seen that there is a great opportunity for storage of renewable fluids as well. And the subsea storage system that we're qualifying has been modified into storage clean energy in the form of liquid or ammonia or e-methanol. So placing the storage solution subsea will actually enable a safer solution. And for storage of ammonia, we will be utilizing the ambient pressure and temperatures already available by the environment. And refrigerated topside ammonia storage solution, they require a lot of energy, and a subsea solution will not require any energy at all. So with this, Hamid, this opened up for a lot of opportunities for other application, as for bunkering of renewable fuels, for the shipping industry. And how does ammonia fit into the picture that you're seeing?
Yeah, of course. We expect ammonia to play a key role in decarbonization of shipping industries in general, with a focus on deep sea shipping. And our forecast shows that the ammonia can and combined with hydrogen could reach about the 35% of the fuel mix by 2050. And ammonia is expected to grow more than hydrogen because of this, the easier distribution, storage, and bunkering system. Of course, the system that you mentioned, the subsea storage system, that would be very interesting to look at this for the bunkering. And another aspect is the compatibility with the existing and emerging technologies for propulsion and power generation. So it's in the future energy mix that we see ammonia for shipping as a bunkering fuel that can play a key role.
So yeah, we would definitely love to learn more, and I think we're learning more and more about this industry every day. So how do you see the ammonia shipping industry evolving?
It's being worked still. Of course, the technology is being developed by both looking at the fuel cell and the engine as well, but it's some technology needs to be developed, and some challenges need to be addressed before, especially towards the hazards and the safety of the bunkering. And also another aspect is the availability of the ammonia. Of course, we know that ammonia is available in many of the ports already because of the using for the chemical industry, but being used as bunker fuels, that requires more safety, as well as a personnel that will be directly is working with ammonia. But it's definitely, we see a lot of activities on both sides, as a bunker fuel as well as for transportations.
Yeah, very interesting. So Charlie, how does this fits in for the Net Zero Technology Center in your view on the future?
So to start with, on the shipping side, to follow on with what was just said, we've spoken to a couple of different shipping companies, and a lot of them say that for long distance shipping, ammonia has won in comparison to something like hydrogen, because that is just too difficult to store and transport. So on one side you've got the ammonia, but some other shipping companies, the likes of, I think, Maersk, recently established a new facility in Denmark for manufacturing e-methanol, because they see that as the kind of fuel of the future for them, or as a kind of stepping stone before they get right through to full ammonia. What's interesting is that we've heard that same story from a few kind of completely different companies. So they're all looking at these things in isolation and have come to the same conclusion. The likes of e-methanol and e-kerosene as well are looking to be like really promising kind of alternative fuels for the future. And we're not involved in shipping in anywhere near as much as the likes of ABS are. So just from those short conversations that we've had, those are the conclusions that we've come to as well.
So did you have anything with regards to the low carbon power solutions that you've been investigating with regards to looking at taking technology elements and putting them together, platforms and wind farms, and how that could be used as a value creation for potential projects?
Absolutely. So we work very closely with the oil and gas industry in Aberdeen and the North Sea, and obviously they are under a huge amount of pressure to decarbonize their operations, there's a real need for them to transition to low carbon forms of energy generation. One of the ways being kind of a full electrification, so that could be a power from shore, a cable running from the mainland out to the asset. What they've kind of rapidly discovered is that that's very complex, very expensive, and it's just too far away in terms of a timescale to meet the targets in the time frame that they require. So alternative fuels such as e-methanol and ammonia are gaining a lot of traction over the last few months. And when we're looking at trying to retrofit these offshore installations with turbines that run on alternative fuel, when it comes to the storage of that fuel, it's an aging infrastructure that have limited deck space and weight capacity. And there are also safety concerns. So, if you're trying to store something as explosive, quite frankly, as e-methanol, do you want that in large scales on top of, on your top side? Probably not. So putting it subsea, it just solves all of those problems in a winner. And for a system such as this, which utilizes, as you quite rightly put, on utilizing the seabed conditions of the North Sea, the pressure and temperature, you can store ammonia, which is usually a gas at ambient conditions, as a liquid, which dramatically increases the energy density. So you can imagine something like that. So the little picture we've got up there, you could imagine a kind of hybrid or partial electrification system where you could have an offshore installation, which could be oil and gas. It could be carbon capture and storage in the future. We've also had conversations about folk that want to use them as Bitcoin mining farms. Go figure. But in order to power these installations in the lowest carbon way possible, having something connected to a couple of wind turbines that can power it when it's windy, and then when the wind dies, they have the the backup with low carbon alternative fuels, and utilizing a system such as yours in order to store those fuels, all of a sudden you start to get quite a kind of comprehensive decarbonization picture for offshore installations. So that's a lot of the pieces that we've been looking at recently, along with a bunch of other people.
Yeah. No, thank you, Charlie. I think this is very interesting on how to take different technology pieces together and to create value. And you were also touching base with regards to other fuels, synthetic fuels like e-methanol. And I was just wondering, Hamid, if you and ABS are you also looking at other synthetic fuels for the shipping industry, or is your primarily focus around ammonia?
No, that's a very good question. Currently, there is no really a single fuel that works for all types of ships. So therefore, we're looking at all alternative fuels, being considered, and then the different pros and cons of the different type of the fuels. E-methanol, of course, is available now, and as just Charlie mentioned, some big shipping companies, they have already ordered a couple of these ships. So, and the main key here is that with the minor changes in the engine and also for the storage system with the minor modifications, they can be used with e-methanol. Of course, that's the question again, is that the supply at the scale with the renewable sources. So we see there are a lot of questions and concern regarding the carbon emission or the greenhouse emission through the value chain. So that's the big question. We are looking at the different type of the fuels and how they are really being, instead of the current from the regulatory frameworks like EU ETS or IMO, we are looking from tank to wake, and that is shifting to well to wake. That means that what was the sources? We need to look at the sources, where is that? So that will that's the big questions. And it's alongside that will be for short sea shipping, long sea shipping. So it's different type of the fuels will be in the future.
I think that's a really interesting point, though. There's no one fuel that will do everything. There's no one silver bullet that we nail that and everything else is fine. I think it's going to be there'll be opportunity for every single fuel out there, depending on the application,
as well as the battery power for the ferries and smaller. Yeah, absolutely.
Mm-hmm.
Yeah, I think this is a very interesting and promising discussion as well, and I also think that it's very nice that we can use the technology elements and maybe like in the near future projects, like for chemical storage. And use those technology elements and the knowledge and the system that we're qualifying into the energy transition picture as well. So yeah, with that, Chris, I was just hoping maybe you could help us to summarize why anyone should join the joint industry project for qualifying the subsea storage technology.
Yeah, obviously the multitude of potential applications is part of it. But from our side, I mean, I made a little list here. Why did we join? Obviously, we like to be on the inside of new technology development, so we can influence it and we can ensure that it meets our requirements. And obviously, that comes with learning. We're actually schedule driven in this particular part. We're usually not schedule driven as much for these technology developments, but this time we are. We do think that the large volume storage is the way to go. I think the 200 meter cube is probably going to be just the starting position. There'll be larger applications as we learn how to do it. And just to say that the ABS role is well received. We like the idea of a third party verifier that oversees the fact that we've done all the necessary risk identification and mitigation. Yeah.
Mm-hmm. Yeah, I agree. I definitely think it's very good to have ABS on board as well to oversee not only what we're doing now but also what we've done previously in the previous qualification step. And I really appreciate Chris, Hamid, and Charlie all the important input and information that you're bringing and the value that you're bringing into this project. And I also hope that everyone listening has found this panel discussion valuable, learning more about the subsea storage technology. And I would just also like to summarize with the objective with the ongoing JIP. We would like to confirm the operation of the system, and we would like to provide evidence that technology will function within safety operational limits. And this means both the functional and performance specifications within, of course, the acceptable level of confidence. And the overall goal is then to unlock a safe, profitable, economical, and flexible product for the market. And the product should be ready by the end of 2023. And it should be designed and built and to suit the customer requirements and the needs that we see in the market. So yeah, thank you all. I'll give the word to you, Shelby, to round it off.
Absolutely. Well, I wanted to mention before we get to some of our audience questions, for anybody interested in joining the JIP or learning more, we have a couple different ways they can reach out. The first is they can email us at subsea@nov.com. So again, that email is subsea@nov.com, and we have it there on the screen if you need that. And then we also have a news story online that you can go and read a little bit more, but also contact us there. And that is www.nov.com/subsea storage JIP. And there we have that URL on the screen as well. So I'd like to definitely invite our audience to go check out that news story and again, read it and then contact us if they would like to, if they're interested in joining the JIP. But with that, I do actually have some really great audience questions that we want to get to. And if you're watching this and you think of another question that you might have, you still have time, you can put that in the comment section. If we're not able to get to it live during the show, we'll still make sure to get your question answered, as well as you can also email us at socialmedia@nov.com anytime with your questions, and we'd like to make sure you get them answered there as well. There it is on the screen. But for now, we want to go for the first audience question, and this comes from Dr. Mahfouz on LinkedIn. And he was wondering about the environmental impact in case of a potential leakage and any plans that you have for mitigation. So can you talk a little bit about leakages?
I guess that question would be directed to me then.
I think so.
So we have the leakage method for monitoring of leakage through the membrane. Is of course it's depending on the fluid which is stored. But it could be monitored and controlled by pressure difference, methane sniffers, inductive sensors, pH sensors of conductivity transmitters, which would be topside then for a closed system. The way it worked when you have the protection structure and the seawater flowing in and out, you will have a valve as well. So when you detect that there is a leakage, you would close and the entire volume will be then captured within the protection structure, and the fluid inside could be extracted then afterwards. And that would be the same with the closed system as well. And then it would of course already be connected to topside, so that then it would be easy to do the extraction from topside.
Absolutely. Thank you. I appreciate that. And this next question, can you talk a little bit, I think you might have mentioned it throughout the show, but can you summarize what chemicals can be stored subsea?
I guess we would like to say all chemicals can be stored subsea, everything like from production chemicals to enhanced oil recovery chemicals. One of our key components is our flexible membrane. So it's depending on the compatibility with the flexible membrane and the chemical that is being stored. And that is also why we're doing membrane service life testing as a part of the JIP. But other than that, there shouldn't be any limitation. We just need to make sure that we're choosing the right material for the flexible membrane during the screening process.
Excellent. And I think this last question came from a user online. They asked, how big do these subsea storage units get? What would the maximum size be for one?
Yeah, I guess that's a good question as well. So as a part of this JIP, we're qualifying storage unit sizes up to 10,000 cubics. storage units, they can be coupled together in what we call a cluster frame, and it's a modular and flexible system, so there isn't any limitation with regard to the maximum storage volume that you can store. But for one storage unit, we're looking at the storage unit sizes from 3 cubic and then up to 10,000 cubics.
Excellent. And I think
that's in the metric. Yeah, I'm sorry. Yeah, it's in the metric. So I hope that you can convert it if you're using other units.
I appreciate that. I'm the worst at knowing my metric conversions, but I always appreciate the clarification. That helps me out. And we actually did get one more question, I think, that we'll be able to have time for, and it is why do we have flexible membranes? Why what's the need for that?
Yeah, I guess I'll take that one as well. So the flexible membrane, it serves like the first barrier. Yeah, so it's a good question. It's helping us keeping the cost down for the entire system as well. Depending on what is stored inside in the membrane, it could be buoyant, non-buoyant, or neutral fluids, but it makes it also possible for us to make one system that fits all types of fluids. Yeah, and it makes it it's a good technical solution for having a dual barrier system with the flexible membrane and then the protection structure. I could give an example for we haven't touched base so much about oil storage, but for oil storage, if you didn't have the flexible membrane, you would have an emulsion layer build up with the contact between the seawater and the oil. And with the flexible membrane, in that case, we're actually able to reduce the size of the storage unit with the 30%.
Excellent. And I think we did just get a few more. And I always say, I think this is going to be it. And I'm happy to spite myself there, just because I want to ask our audience's questions as much as we can. So, and I also, sorry, Julie, for putting you on the spot. You are as the engineer, we're going to ask a lot of those. But let's see, on LinkedIn, this question came in. Can this be used to store crude oil as well, considering all the different mitigating factors in place?
Yeah, I guess that I touched a little bit upon that in the last example I gave as well. Yeah, so crude oil and condensate, that was actually what we started with. So yeah, definitely can be a replacer for a floating storage unit and then having a subsea oil storage or condensate storage as well.
Absolutely, and just to take the pressure off Julie a little bit, I'll just jump in here for a moment and say that the previous project phase that we were involved in was looking at, it was a subsea oil storage system. And then throughout that phase, when the energy transition was really starting to heat up, we as the project consortium realized the potential other uses for this system. And that's when we kind of changed the key usage to a subsea energy storage system in the form of ammonia and other alternative fuels. So it's really been on a bit of a journey, the technology. But I think it's a really good story and a really good example that, you know, technology can be adapted for new purposes, new applications. So yeah.
Absolutely, thank you. And like I said, I'm going to keep going for a couple more. I got the green light on our production side. So can you talk a little bit about what the material consideration is for this storage?
So would it be for the storage unit itself or the entire system? But I guess what I would say, it's depending on the fluid that is stored. Usually the focus point for us is the flexible membrane, as it is the new component. The other parts of the system, they are well-known components. We've done a lot of work with regards to evaluating different materials for the protection structure itself, mainly then evaluating and looking at the concrete or FRP or steel for the protection structure. where we have for the larger structure, definitely a huge benefit with going with an FRP or GRP solution. And for the smaller units, it could also be for some cases that still will be the competing choice as well. I hope that answered. Otherwise, yeah, please follow up with me, and I'll try to answer in more detail.
Yeah, exactly. If any of these questions, if anyone wants more of a deep dive, like I said, you can email us at subsea@nov.com, social media at nov.com, anywhere, and we'll make sure to get you in touch with Julie. And then I think now we'll say, just for time, we'll do one more question. But there's a few more I see that are great in there. So if you did comment your question, don't worry, we'll still get that question answered. But as far as on the show, we'll finish it up with Carlos on LinkedIn asked, are these systems being tested to any type of hurricane or kind of weather consideration?
So we have it as a part of the risk assessment, and then we have, then we're doing a lot of analysis with regards to the feasibility studies that we're doing. But for the shallow water testing that we're doing, it's in a pit in a controlled environment, and then other environmental aspects with regards to if it's currents or wave or harsh environmental conditions in general. That's the part of feasibility studies that we've done and risk assessments that it's been going on in parallel.
Excellent. Well, with that, I think we'll close out audience questions. And I just want to say, again, I know I think we've said it a lot, but can't be said enough. Julie, Charlie, Chris, Hamid, thank you all so much for coming on the show. This was an excellent panel. I think I've learned a lot. I know our audience has learned a lot as well. And it's been a really great in-depth conversation. So thank you all so much for joining the show today.
Thanks for having us.
Thank you.
Thank you for having us. Yeah.
Absolutely. Well, and that will close up our show today. Once again, thank you so much for joining as our audience. And again, if you have any questions, you can reach out to us at social media at NOV.com. You can also check out all past episodes of this show, as well as our other show, Inside Out Horizons, at NOV.com/live. So check that out, watch all of our past episodes, and look forward to seeing you next time. Thank you.